for today's webinar on open source best practices from continuous integration to static linters. We had more than 150 people registering for this webinar. The webinar is going to be presented by Daniel Smith and Ben Pritchard. They are from the Molecular Sciences Software Institute. The goal of the Institute is to serve as a nexus for science education cooperation serving a wide community of computational molecular scientists. It includes biomolecular simulation, quantum chemistry, and material science. Ben has a background in computational chemistry. He got his PhD from the University of Buffalo, and he has a passion for computer programming. He has been working on the accuracy and the precision of computational chemistry calculations. He's also interested in long-term maintainability and reproducibility in computational sciences. Daniel has worked quite a bit in projects like open source scientific projects like NumPy and Psi4 packages. And also he has an interest in educational outreach through the software carpentry and the educational activities offered by the Molecular Sciences Software Institute. His research interests currently focuses on community databases for quantum chemistry. And the idea is to add in the generation of molecular force fields, artificial intelligence research, and novel method performance assessment. So as you see here, we have links for the Google Doc where you can enter questions for Dan and Ben. There is a survey at the end also that would like you to give us some feedback. The slides and the recording will be available next week, and you have the two links there where you'll be able to find the slides, the recording, and also the questions and answers through the webinar. So with that, Dan and Ben, please, you take over.
Great, Osni, thank you for the introduction. One moment. All right, can you see our screen?
Yes.
Yes, great, thank you. So as Ozzy mentioned, my name is Daniel. Ben is joining me to present some of our open source best practices that we view. Before launching too much into those, I thought we'd give a brief overview of the multi-year so that you can have a general idea of effectively where we're coming from. So as Ozzy mentioned, we're mostly focused on computational molecular science, where computational molecular science is everything from quantum chemistry and quantum materials all the way up to coarse-grained molecular dynamics simulation. So any kind of computational aspects dealing with molecules, we are in this area. And I think one of the unique things about us is that MISSI is really aiming to serve and enhance this community. So we're not really out to build, for example, like new molecular dynamics or new quantum chemistry packages, but how can we build software that's the base infrastructure for all of these packages, or how can we help them become more sustainable is really where we're focused. So we are only about 2 years old at this point, a little over at this point, and we are funded by the National Sciences Foundation Software Infrastructure for Sustained Innovation grants. And so because of this, MISSI is the institute level grant of this, along with a couple sister organizations such as the Science Gateways Community Institute. And so these are kind of a new effort by the NSF to say, can we take effectively, instead of single PI grants or multi-PI grants, but actually make institute-level organizations within these fields for the greater good. So we're a bit different than I think you'll normally find. In addition, we are a collaborative effort by many universities across the United States, as you can see listed here. We are formally headquartered in Blacksburg, Virginia, with 12 software scientists locally. We also have software fellows programs where we support around 20 graduate students and postdocs across the United States. So if you're interested in one of these fellowships, I suggest you should look into one of our websites, and we'll give you a link at the very end for So to give you kind of an idea of what we do, so as I mentioned, we do build quite a bit of software infrastructure. So we have projects ranging from the ability to transform different molecular dynamics inputs into other inputs. We also have things like large-scale quantum chemistry databases and so on. So we do build quite a bit of software ourselves. We also have a lot of education and training. So we have quite a bit of online materials and tutorial guides, which we'll give links to at the very end, which I hope you'll peruse. And we also host quite a few workshops. So these are either these kind of like 2-day boot camps that we hold around the country. We also have these 2-week-long summer schools. And then we do a host of other more targeted education programs depending on exactly the needs of a particular audience. And finally, probably one of our most important things is the community outreach and engagement. So we spend a lot of time talking to our community, trying to figure out data standards and best practices. And we also try to effectively get a little bit more cohesion in API and data standards so that things are a little bit more transferable and interoperable and effectively more usable in our particular space. So we do a lot more than this, but I think these are the 3 main thrusts that we want to go over. So I think that's all I really want to talk about at MISSI, because this is really about our software open source best practices. So when we were putting together this talk, what we did was we've been going to these webinars for quite some time, and we see all these terms thrown around. And I think we agree with all these terms across the board, but what we wanted to do is spend a little bit of time illuminating what would an example of best practices, DevOps, and open source be. So we went through all these things, and we want to give these kind of like concrete examples. In addition, one thing that we see a lot, but we haven't really quite seen mentioned, was this just get the physics working when it comes to software. So a lot of times we have software that are designed by a graduate student for a specific project, and the question becomes, if we need to maintain the software, we need to edit it later, what are some practices employed so that we can spend a little bit of time up front to save us a lot of time in the long run? And this is really what these open source best practices are about. And on the term best, I think this term is thrown around quite a bit. And so I think this is a completely subjective term. So I think that there are a couple of practices that we think are very core to all best practices. But this really depends on your community, your audience, the kind of software that you're building, et cetera. So we kind of want to give an overview of different possibilities of best practice. And again, this talk is really about practical applications, because ultimately with best practices, the idea there is to make your lives easier. So they do take a little bit of time, but the hope is that overall it saves you quite a bit of time in terms of software development. So to begin at the very top, we want to talk about what open source is. So there's an organization called the Open Source Initiative, which in some ways is kind of a single definition of what open source is. Of course, open source being open source, there's not a single definition, but many. But I think this is a very reasonable starting point to kind of discuss this particular topic. And so OSI has come out with this very legal sounding statement of exactly what open source is. And I guess from our perspective, it really kind of hinges on 3 really major points. So the first one is going to be free distribution and charge of the program. So effectively what this means is that a lot of the open source codes that we find, they're distributed by many different people in many different contexts. So I think a good example is one of the programs that we work with a lot. You can find it on things like Ubuntu and Fedora's package manager, which the primary authors actually had nothing to do with, and it was supported by people interested in those particular regimes. So having it free and open charge and easily distributable is very key. The other thing is that the source code is freely available. And what this means is that anyone can go to a website without any kind of contract or license to examine what the source code is. And we're seeing this more and more in so many different industries, not only the scientific one, where tools like version control tools like GitHub make the viewing and editing of source code extremely easy to do. And the other thing is going to be basically the application of derived words. So I think there's many cases that we've seen where perhaps the primary authors of this work did not have one particular feature that someone else needed, so they modify the program to best suit their needs. We always hope, of course, that these features will come back to the primary program, but sometimes they do not. But I guess from our perspective, this is really the three main pillars that open source really revolves around. And if you want to look into all the individual details of what the open source initiative defines as being open source, I would encourage you to look through their website. And so we want to talk about what are the benefits of open source, both from a community point of view and a personal point of view. So I think from a community point of view, open source actually allows you to build these communities very easily. Because they're completely open that anyone can join, it becomes trivial for someone who's not normally part of your ecosystem to go ahead and start making changes. And in fact, a lot of what our best practices around is both making it easy for users to make changes and making sure that the changes that they make is very beneficial to your code. The other thing that we really find is that open source really allows this common goal execution. So there's quite a few examples as seen below. So everything from the Apache to the Linux Software Foundation, which rely on open source and basically this common goal, where everyone from open source developers to commercial entities often contribute to every single one of these very large programs that we have shown. I think things like the Linux Foundation are particularly in this category, where with Linux you have tons of open source developers in very many aspects, but then these days there's quite a few developers at companies like Microsoft and Apple which are contributing to these core programs. So if you can build an ecosystem of this size, you get an enormous benefit from it. And then from a personal point of view, I think here at MISSI what we found is open source really helps with coding skills. There's so many cases where a single person coding doesn't really get a lot of review and feedback. But this is actually one of the main pillars of open source. You constantly get feedback on your work and how to improve. There's also this enormous, basically, user base that can look at and comment on different approaches. So you have so many different people coming in and saying, well, this is the tool that you're looking at, but you might want to suggest this one to see if it matches your use case. And so it gives you a lot of power to find really the right tool for the right job. We also have a lot of peer recognition involved. I think one of the really nice things is that people can always see exactly what you've done. So if you're applying for some sort of company and you want a resume, almost always some sort of open source version controlled software is going to be a part of it. Because most of these companies actually use some sort of version control internally, so you're able to practice something in a very public fashion that people can evaluate and have a much better idea of what they're getting in terms of a software developer. So I think these are both the community and private reasons to look into open source. And with that, I think we're going to dive a little bit into version control. But before we do, I wanted to see if there are any questions that we can go ahead and answer.
So far, there are no questions in the Google Doc that we haven't answered thus far.
Okay, great. So in this case, I'll turn it over to Ben for a little bit, and he will talk about version control.
All right, so first we want to talk about version control. So what is version control? It is a program or a set of programs that tracks the changes to the code over time and who makes those changes. This is very important. This is going to be the main way that you interact with your code and how the community interacts with your code. A lot of times I've seen in scientific software, you might just have comments at the top of the source code file, and the comment is just somebody's initials and what they've done. This does not count as proper version control. So by far nowadays, Git is the most popular. There are others, Subversion or Mercurial, but in general, we really recommend Git. Git itself can be fairly complicated, and we really recommend that you take the time to learn Git or whatever version control you're using. So for Git, I know there are lots of great tutorials. There's lots of good YouTube videos. You can take a boot camp on it. Really take a day or two to learn it, because this is going to be an extremely important tool for how you are interacting with your code. This is a foundation of your community, and you really should learn it. So in the figure, you can see a Git history that I've taken from a fairly popular project. It's a Sci4 project. And you can see, who's committed what and when they committed it. This allows you to, assign credit, as Daniel mentioned. Credit is important in our field. On the flip side, you can also assign blame if somebody makes a mistake. Somebody commits bad code, you can see who did it and when. Git repositories are often hosted on the cloud. So there's the logos of 3 popular services there at the bottom: GitHub, GitLab, Bitbucket. GitHub is by far, I believe, the most popular. But there are many projects that are using the others. So we've all downloaded something at some point, and the first time we try to run it, it doesn't work or it breaks. Mistakes in software. This is a quote by Neil. Mistakes in software erode trust in research and researchers. And Neil gave a presentation 2 presentations ago about this kind of topic. So one of the ways we can improve the reliability and make our software much more trustworthy is with testing. There's lots of different ways you can test code. So I have, 5 different categories that it's commonly broken down into. So unit testing is where you're going to test a very small portion of your code, usually a function or maybe a small class. Integration testing, you're going to test the interoperation of several units together. Regression testing is one that is less commonly done in science. That is where somebody submits a bug report, you fix the bug, you create a test to make sure that that bug is never reintroduced again in the future. So it's obvious somebody is doing something that is now depending on that bug being fixed. Add a test, make sure it doesn't happen again. Smoke testing is what I believe a lot of scientific software does almost exclusively. And that's where you're doing a sanity test of the entire system. Does it crash? Does it get the right answer? And then acceptance testing is something that is also somewhat commonly done. You test that a feature is correctly implemented. So you add a new feature, you add a test. And that is highly recommended by us too. One thing that is commonly missed is testing of failure modes. This is something that we encourage, but you don't have to go overboard. So what we mean by testing of failure modes is when you give your software a bad input and it should fail, does it actually fail? Or does it keep going? Does it do something completely unexpected? There's lots of different ways software can fail, so you can spend all your time writing tests for failure modes, but just a couple quick sanity tests that your code fails when it should can really be helpful. Okay, we all know we should test. We know what we should test. How do we test it? Depends on the language, depends on what's in vogue at the time. Our recommendation is generally just to pick a common, appropriate testing framework and do not write your own unless you really have to. And it's going to be very rare that you have to write your own. So these testing frameworks provide a lot of features. They provide, segmenting or grouping tests into categories: slow test, fast test, maybe feature test. They usually have timing. Usually you can detect failures when exceptions are thrown, seg faults. So there's lots of features that these provide that should be useful. So some popular ones for C and C++, if you're using CMake, we recommend just using CTest. Catch2 is another up-and-coming testing framework. For Python, of course, the standard is PyTest. And for Fortran, again, you can build Fortran with CMake. So if you're using CMake, again, use CTest. So the figures show, these are outputs of a PyTest and a CMake CTest run, and all the information that it can give you. Okay, so now you know what you should test, and now you're testing them with some sort of testing framework. What can you do with it? Well, you can set up something known as continuous integration. And in here, testing is done automatically when commits are made, usually to your cloud-hosted repository. One common feature of this is that the results are displayed publicly. So you see in the figures, there's a badge for a build, so passing or failing. Displaying it publicly really develops trust in your software package, and it really makes developers feel safer in contributing. So if you're a small, a single-person developer, and you have an idea for a new feature to add to a large package, you might be a bit hesitant because you think you might end up breaking everything that's already there. But if that big package has thorough testing, well, you can add the code that you want to add. As long as the tests pass, then you should be okay. And if it does have thorough testing and you do add something and it does break the big package, well, that's kind of their fault for not testing properly. So yeah, people add badges. Badges are pretty popular. It's also an incentive to really fix. So if builds are failing, you get this big red badge. When I see that on my project, I really feel inclined to fix that as quickly as possible. So you don't have to just do testing with CI. There's a couple different things. You can build documentation, upload documentation. One thing you will sometimes see is continuous deployment, which is where you do your continuous integration step, your testing, your building, and then you will actually deploy a service. This is not common in scientific software, but it's a term you should be aware of. So this is common in something like you're hosting a web service. So every change you commit ends up being reflected in the web service. Some common features of CI matrix builds. This is where you can test different permutations of different features. So compiler versions, compiler vendors, Python versions, library versions. Again, this can go overboard with all different combinations, but you see the example there. This project is testing with Clang, with a certain Python version, and GCC with a different Python version, and GCC 6 with a different Python version, trying to cover a lot of the common permutations of Python and GCC that are out in the field. So you can test different distributions, operating systems, different versions of dependencies. CI is usually integrated with your version control, so it is very seamless with GitHub and GitLab. And it's often integrated with social services such as Slack. You can have it pop up the message in Slack when builds fail or succeed. You can get an email when builds failed or succeed. So integrations are very popular with developers. So this leads to a very common development workflow, and I am glossing over many details. But the workflow is commonly called the fork-pull model. So in this model, the developer is going to fork the master repository, which means he's going to make a copy of it locally for himself. And then they are going to develop on it. They're going to hack on it, add their code, modify the code, and then eventually they're going to submit a pull request, which tells the developers of the main package that they would like to merge their code back into the master branch. And then within the pull request, there's going to be debate. Do the test pass? Is the code quality good? Is it formatted correctly? Is it a feature that's really needed? And then if it is accepted, it will be merged back into the master branch. So key features, right? The development happens on an independent branch and repository. And it's common to see projects where modifications only happen in these branches. There's nothing ever committed directly to master. Yeah, the code is reviewed and tested. Again, those tests you wrote are actually very useful. And then if it's accepted, the code is merged in the master branch. The commit authors remain along with their commits, so they get credit, and it shows up in the master branch.
And so I think this kind of fulfills kind of like what we think is like the primary pillars of open source, is having testing and CI along with some sort of version control in this kind of workflow. And if we look out at virtually any project online that's open source, they almost always follow this kind of pattern. And at the very end of the talk, we'll give you quite a few different code bases that are kind of like big quantum chemistry or molecular dynamics codes online, which you can kind of see these best practices being applied to. And I think this is also the end of what we think of as like the truly core best practices. So I think it's safe to say that these best practices are extremely transferable across any domain and any feature set. So I would encourage you to look into them, and we'll also give you links to tutorials if you'd like to supply, if you'd like to do some exploration on your own. And at this point, we'll probably take questions if you have anything.
Yeah, yes, there is one question, Dan. I've been using CPPU test. Should I switch?
So CPPU test is really great for C projects. It is primarily a C testing code. And I would say that it's completely up to you. If you're really happy with it, then you probably do not want to switch. If you have some features that are missing, you may want to consider switching. I think one of the big things is that, I'm sorry, we're getting feedback. Okay, great. So what we really try to exercise is use whatever is useful to you. You know, if it's a huge investment to switch and it fills all your needs, then there's no reason to switch. I think something like catch2 is really great for modern C++. So if you're C++ 11 or above, then you might want to look into it. If you have a pure C code, then catch2 probably isn't quite appropriate. So it completely depends on your circumstance. And if you want to talk about pros and negatives more, we're happy to chat if you want to reach out to us.
Okay, so there's one more slide on CI, and that is, what services are available to actually help you do your continuous integration. They can be cloud-based, or you can use your own hardware, and many or most of these are free for open source projects. Okay, so cloud-hosted Travis is very popular on GitHub. Circle CI is a similar competitor. They both use Linux and OS X. If you are building for Windows, then you can use AppVeyor. Azure Pipelines, I guess Daniel can attest to, is very powerful and very flexible, but with that power and flexibility comes complexity in setting it up.
Highly complicated, but extremely powerful.
Very powerful and very generous, I hear, in their resource allotment. For locally hosted, if you have special hardware that you need to run on, you might do this with GPUs, or if you have very, very stringent requirements. Jenkins is probably the most popular, just completely open source one. You host it yourself, you host the hardware, and it will connect to GitHub and run the CI on your hardware. BuildBot is another one. It's very flexible. It's written in Python. It's probably the most flexible one I've used. but sometimes, integration is a bit iffy. TeamCity is kind of a hybrid. The dashboard is actually cloud hosted, but you can run the build tasks on your own hardware. So you can download a package onto your server and then connect it to your TeamCity dashboard that's in the cloud. So those are the ones that we consider most popular. I think Travis is probably by far the most popular.
And so there's one quick question that asked us if there's any cloud-based CI services that include GPUs. So not at the moment. NVIDIA is trying very hard to spin up an NVIDIA-based cloud CI service. I unfortunately do not know the current status of that. I think by far and large, if you need GPUs, most people use local machines with one of these locally hosted CI services by far. The other one is GitLab CI. So we do like GitLab CI quite a bit. However, I think we find it perhaps almost a little bit more limiting than we'd originally hoped. So it really depends on what your use case is. It's hard to say too much about all the different CI services without knowing exactly what each project's doing. But I would encourage you to kind of always evaluate what is the feature set that you're looking for, what are the pros and cons with each of these CI packages before moving it. And another question is, yes, so supercomputers are beginning to allow CI-like services. So when we talked about testing, we mostly talked about effectively some sort of application-based testing. But another piece of testing that we probably didn't talk about as much is integration testing. More importantly, regression testing on these big machines. It's very hard to tell, for example, if some sort of code change effectively made running on 4,000 nodes slower or faster without actually doing that. So testing can get quite complicated, and so mostly these CI services are kind of like your initial stick test. So does the project build? Does a reasonable set of tests pass? But unfortunately, for running on really large HPC resources, there's still really no substitute besides actually doing that. I think we should probably move on. I think there's a lot of questions, and we might be able to answer some at the end. Does that sound okay, Ozzy?
Yes, it does.
Okay, great. So as we mentioned, we believe that these were kind of the really core things that most projects that are open source should be looking at doing. We think that they really help build trust, both from a community standpoint and from a new developer standpoint. One of the biggest fears that we hear from new developers is simply the fact that they're worried about breaking a piece of code. The second largest fear that we hear is, of course, they're nervous about putting their code out there for anyone to review, which is a bit harder to overcome. But in terms of breaking the code, we really find continuous integration to be very powerful, because what we try to tell users is that if it successfully builds on your continuous integration platform and anything breaks after that, that's the fault of the primary developers and not any kind of new user or new developer issue. And on this, one thing that basically helps projects quite a bit is going to be code coverage and trying to analyze how well that they're doing in testing. So oftentimes we find that projects that do not have code coverage spend a lot of time testing a very small percentage of their code and have very large swaths of their code being untested. So I'd like to mention about this code coverage. It effectively measures what percentage of number of lines of code ever tested. And two important things about this is that 100% code coverage does not mean that your code isn't perfect by any stretch of the means. This is simply a heuristic, seeing how much of your code is covered. The other thing that we like about it is that it's a very hard metric to fake or to accidentally do very well on. Almost in every single case, you actually have to really cover a very large amount of the code to have a good score on this. And so to give an example of code coverage is I pulled off one of these starburst patterns that we see in a lot of these coverage testing tools. And so these really bright green areas mean virtually 100% testing, and every single little notch either means a folder at the inner level or actually an individual file at the outer level. And so we can see from this kind of starburst pattern that there's individual files that are virtually 100% tested, but these really dark red actually indicates 0% test coverage. And so this kind of gives you a quick overview of how well you're testing your code or not, and it also gives you places where you might want to consider writing tests. So this is why we like code coverage. And so this is kind of an example of like what one of these code coverage tools will do, the online versions of them. And in this particular case, I think a lot of times that we see is people miss various if statements. So they usually only test like one particular branch of the pathway. Sometimes this is okay, but it's always worth at least looking into. And the other fun thing is that exceptions are often not tested in general. And what we find quite a few times is that because these exceptions are never tested, people actually evaluate into these code paths when an exception should be thrown. So instead of getting a nice error message, they actually get some sort of segmentation fault or the like because an incorrect branch was evaluated. So code coverage is pretty easy to set up and kind of gives you a general idea of how well you're doing your testing. So there's a number of services online, such as CodeCov and Coveralls. There's tools for virtually every interpreted and compiled language that we're aware of that will do code coverage. So it's a fairly popular thing out in the world. Another thing very similar to this that we find to be very helpful is going to be code formatters. And so what a code formatter does is they turn all of the code into a very systematic piece of software where the indentation style, where I put a bracket, etc., is the same throughout the entire code. And particularly for open source, when you have a lot of developers working on this code, or when you have someone new to your code trying to look and see what it does, this is very helpful because it provides kind of like this uniform look and feel to a code and reduces the overall cognitive overhead of trying to examine and figure out what it's doing. So we believe these things are really quite nice for open source. They're also really nice to use. They usually integrate with IDEs. They also have command line tools which will just automatically format an entire project with one line. One of the interesting things about this is that several languages have a single standard. So for example, Python has something called the PEP8, which effectively everyone uses within the Python world. But then languages like C and C++ actually have multiple standards depending on who you talk to. So for example, like C++, there's Clang and GNU style and Google style code formatting. And each of them are relatively similar, but still a little bit different. For example, like a tool to format C++ actually allows you to pick between them. And from our standpoint, it really doesn't matter which one you pick, but we do believe that actually applying a code formatter to your entire code base does make it more readable and a bit more friendly to new users, which is going to be very important to your ecosystem. Again, these things are quite widely developed, so we're able to find ones, again, for virtually any compiled languages, simply by Googling code formatter plus the language that you're interested in. For us, we really like Clang format for C and C++, and we really enjoy YAP for Python, YAP being yet another Python formatter. And so I believe those two tools, we see them a lot in open source projects, clearly not as much as the continuous integration and testing, but still I'd say in over half the projects that we encounter. The other popular tool that I'd still say is experimental is the static code quality analysis tools. And so what's nice about them is they're able to examine the entire code base without any kind of testing or writing tests yourself, and they kind of iteratively go through and try to find known bugs, so things like buffer overflows or unreachable code, automatically for you. And this is really nice from a kind of reviewer point of view, where you can rely a little bit on the static analysis tool to kind of get like all of the simple errors that new pull requests or even yourself might make. And so it kind of removes a little bit the cognitive overhead of like, oh, maybe I have a new pull request that includes this new module. Well, do I need that module or not? Well, a static analysis tool will immediately tell you if that was an unneeded import or not. The other thing that we like about it is it helps keep basically reviewer pull request maker relations very easy. It's a lot harder for a reviewer to say, hey, this thing's wrong, this thing's wrong, and this thing's wrong. And one of the funny things that we found over time is that bad news is always easier from a bot. So it's a very nice way of kind of getting all the base and sort of easy errors to basically make sure that your code continues to be clean.
Okay, so question, do we know any good static analysis or linters for Fortran? I don't.
Yeah, unfortunately, for static analysis, we do not know a static linter for Fortran yet. Any other language, we have one, and it's certainly possible that we might be able to get static linters through basically the GNU ecosystem because they seem to be effectively expanding these kinds of things. So we have formatters for it through the GNU ecosystem, and we'll see, I would say, on that. I wanted to give just a couple little examples of what code quality does. So for, I think a kind of a popular error that we see is that I might redefine access inside of like an external scope and an internal scope twice. This is kind of hard for a human to catch because it basically means that I have to like understand all 40 variables in the external scope and all 40 variables in the internal scope and look for mismatches. For something like static analysis, it's very easy for it to pick up, and so it can always find these in a very simple manner and alert you to them. The other thing that it's nice at is looking for potential errors. So probably the most common one that we see in compiled languages is possibilities of buffer overflows or the like, which it has been really quite nice because it catches them all. Like it doesn't even catch like 40%, which a human might, but every single possible case it at least alerts you to. You don't always have to make a change, or you don't have to modify the code, but at least you're aware of possible errors that kind of creep up. In addition, we found that static linters will also catch higher level issues. So in this particular one, it caught this potential code duplication, where if I looked at this list final energies function and list final molecules function, I found that the code was actually 90% correct. And what the static linter is telling me is that I should probably refactor that into two functions that call a common function at the end of the day. And in fact, is what we do. So we're finding static linters to be quite useful. I would still say that they are fairly experimental overall. We're finding them useful, but there's also cases where they're not quite right. And I think one case where they're a little bit not quite right is they can be overzealous in their warnings. One service that we tried effectively was very concerned about cyclomatic complexity, and effectively any function that was more than about 100 lines threw an error. And I think in most code, having individual functions below 100 lines is probably doable, but in most scientific code, it seems that individual functions are often much larger than that. So trying to find a static linter that's more specific on your domain is going to be more difficult than perhaps something like CI, which is extremely general. For us, we are really starting to like LGTM. These folks have been around not too long, but we believe the tool kind of hits like just the right stride of trying to give you enough information without overwhelming you or throwing too many errors. What's nice about it is it's able to do hybrid projects. So this is a LGTM on a project that actually has C, C++, JavaScript, and Python all in it, and it was able to apply LGTM analysis to every single language there. So there's LGTM and CodeClimate and PyFlakes depending on various languages. As I mentioned, I found them for most languages out there, but unfortunately not Fortran quite yet. But hopefully sometime soon someone will get that out there because these tools are constantly improving and expanding. Yep. And so I think these are the tools that we find really useful. But as we mentioned at the beginning, there's such a litany of tools out there. So what we did was we pulled up a GitHub Marketplace to give you an idea. There's probably 120 tools on this website that you can use free of charge. What is nice is almost all these tools are actually commercial products, which are given to you free for open source code. So everyone gains quite a bit out of them. So there's things like different kinds of dashboards. There's agile boards if you do agile processes. For us, we're getting more into web servers, so vulnerability checkers for like SQL injection. There's things like this. Stuff that does dependency management to watch for dependency changes and does automatic increments and the like. So effectively, if there's something that you need, there's probably a tool out there for it. I guess my only caution is, again, you really want to evaluate any tool before you bring it in, and as you bring it in to make sure that it's actually saving you time. I think you can certainly go overboard on these tools where you spend far too much time dealing with the tool itself rather than writing your code. And really what this is about is enhancing your ability to write software and making your software more sustainable and more friendly to either yourself developing in the future or someone else developing in the future. So again, always evaluate if these things are correct for you. Before I jump into the next section, I want to take questions real quick, if I have anything that I can answer.
No, I think you can continue.
Okay, great.
We'll take a look back. We'll go back to the questions at the end.
Okay, good. So there's a lot of open source best practices, and trying to do all these completely from scratch, especially on your own if you're not used to them, can be fairly complicated and a little bit tedious. So one of the things that we try to do is we try to build cookie cutters. And so what a cookie cutter does is for a given language, it attempts to set up a project and I quote, the right way. And of course, as we discussed, the right way can mean many different things to many different people. But in this case, we have a cookie cutter that we believe is appropriate for the Python language for the computational molecular sciences crowd. And so what you can do is you download this cookie cutter. You answer about 6 different questions, ranging from do you want to use pip or conda, which are popular Python dependency managers? What kind of open source language? What kind of license do you want? You can pick your own, of course. And what it'll do is it'll go ahead and it will set up the entire project for you. So it'll lay out the Python in a canonical way. It'll build all the initial files that you require to actually get the project off the ground. And it'll also build things like a dev tools folder, which will allow you to push your project to dependency management systems. It'll set up all the continuous integration, testing, code coverage, and documentation for you. And so from looking at a lot of projects, Python projects online, including things like the NumFocus organization, which houses things like SciPy and NumPy and IPython and the like, we kind of said, what are the best practices that these guys employ? What do our users need? And this is the result where you can set up everything that falls underneath our best practices in, I'd say, about 5 minutes if you're used to it. Or about 20 minutes if you've never touched these tools before. So we're trying to make these things very friendly and very easy to use. And of course, if you use them and you had any issues with them, you can always make actually an issue on that GitHub repository, which contains it, or you can feel free to email Ben or I, and we will attempt to help you through it. So worth checking out if you like the Python language, and we'll get you quickly up to speed on all the topics that we discussed. So I'd say in summary, the main tools that we're really looking for is version control, which helps you build community. It helps new users build out their effectively their resume. We think that testing is probably across the board an incredibly important thing to do. Really gives you an assessment if your code is correct or not. And so many times we've seen very small changes effectively invalidate large parts of these code bases. So testing is very crucial. Continuous integration, again, this is extremely important for building a community. It makes sure that new developers feel very comfortable contributing to your code. You can also test such a range of different build systems on different OSs, different compilers, etc. Automatically, so it actually saves quite a bit of developer time as well. So again, we think those three are kind of the best practices that kind of move across the board. Code coverage and formatters, we think that these tools everyone should at least look into. We think that they're very useful. So I think those are the big five, and of course these new static analysis tools are kind of on the edge. So we'll see how they work over the next 6 months or so. But again, the whole reason for doing this is it really aims to save developer time. It takes, you know, at the minimum, you know, 10-15 minutes to set these things up. If you have an extremely complicated code base, you can usually get them up and running in a day. But at the end of the day, that we hope that it saves you time, which is the biggest thing about these, is it tries to catch errors before they happen, and it tries to alert you to errors that do happen. The other thing is we found that these ideas and these tools try to make it welcoming to new developers, which is crucial for open source to work, because you would like to effectively share the load in managing and developing these big codes. And if anything, I'd stress that all these best practices are always this balance of developer and user time. So whenever you're looking at these tools, always evaluate them carefully to see if you want to pick them up and making sure that they're absolutely right for you. And I think Neil from SSI who talked about these communities to practice. And I just want to come back to this real quick and say that, you know, this best is very subjective and depends on your individual community. So these are a couple of organizations on the right-hand side that we look at. So they're the organizations that we talk to, that we interact with, and we share our best practices with. But again, this best really depends on, you know, what is your target audience, what is the size of the project, and what is the activity level of the project that you have. But we really do hope that these are core good ideas, or we think are virtually important for every single project out there. So you know, look into our tools. We have plenty of guides online, which will give an example at the end. Each of these organizations also provides tons of tutorials and information if you're interested in these practices as well. And for our particular, basically, community of practice, we have a couple codes up here that employ these best practices. So in the molecular dynamics regime, there's LAMMPS and OpenMM. And you can see that both of these codes are on GitHub. They employ CI through various means, depending on their builds and requirements. For quantum mechanics, there's NWChem and Sci4. Again, they have GitHub and CI and code coverage. And if you click on each of these, if you have the slides, it will take you to the GitHub page where you can see exactly how these codes have applied these best practices. You know, what are the small details that they did, and how do they present them to the user. So I would encourage you to look into each of these if you're interested in this practice. And I wanted to point out 2 additional Python utility codes. If you have things that are in pure Python, it's usually a little bit easier to go a bit farther in terms of like code coverage and static analysis. So if you want to look into examples that try to cover everything that we touched on, this opt-Einstein package for tensor order contraction and QC-Fractal for large-scale quantum chemistry databases are 2 tools to look into to see how they apply these practices. And so with that, I think I've covered everything today. If you would like to see more about our best practices, the cookie cutter or emailing list, all are links on this particular page. And we thank you so much for your time, and we look forward to any questions that you may have.
Thank you, Dan. Thank you, Ben. I was looking here at the Google Doc. I think you answered all the questions, I believe. There's only one that I don't recall, a question related. What about GitLab CI? Have you?
Yeah, so we use GitLab CI occasionally. So for example, I think another project that we could have linked to on GitLab that uses this is something called libxc. Which is a really great program which effectively gives access to hundreds of DFT functionals for quantum mechanics. And so I know that one in particular uses GitLab CI pipelines. GitLab CI pipelines are in general pretty generous in the amount of CPU time that they provide. And it depends on your use case. If you're there in GitLab, then you probably want to consider integrating those. If you're on another service like GitHub, then you have kind of like the whole breadth of tools to integrate with.
Okay, so there is one related to the Oak Ridge CI capabilities, but we'll answer that in a different way. So what we're gonna do, we'll ask Dan and Ben to go over these questions and revise the answers. And next week, we're gonna send a link to everybody with the recording and the questions and answers. Ashley, would you like to open the mic for a few minutes, or?
Yes, so since we still have 5 minutes, if you would like to unmute yourself and ask your questions that way, we have about 5 minutes before we have to leave. So if there's any pressing questions, please do unmute yourself. All right. I think we're good then, Osmi, if you want to pull up your final slide.
Yes, just give me a minute here. Yes, so again, thank you all for participating. So I'd like to remind you, if you're kind, would like to have your feedback here so we can improve this series. And again, the recording will be available with the slides and the questions and answers by sometime next week. So the next webinar is going to be on December the 5th, and David Bernhold from Oak Ridge National Lab is going to talk about software licensing. The link is already there where you can go and register. We are not going to have a webinar in November because of the SC18 conference, and a number of people, or almost everybody, working on this project. The IDEAS-ECP, I think lots of people are going to attend that conference. So then again, the next webinar is on the December the 5th. It will be by David Bernhold on software licensing. Thank you very much. Thank you, Ben. Thank you, Dan.
Thank you.